Hello, welcome to the 10th week of this course. So in the past 2 weeks, we were learning about hypothesis testing for a single sample problem and a two sample problem. So hypothesis basically refers to the claim that has been made about the population parameter, and in order to test that claim, we conduct this hypothesis testing. Now, if you can recall, in all the results that we studied in the previous 2 weeks, we were assuming that the population under consideration is normal. So even if we considered for the single sample problem, or when we considered even for the two sample problem in the the previous week also, so there also we considered that the populations are normally distributed. Now it might happen that the population is not normally distributed, or it might have some other distribution, like suppose it might be following Poisson distribution or exponential. And at times it might even happen that you do not even have any idea about the distribution. For instance, you are clueless about the distribution. You just have the data and now you want to test the claim that has been made, or you want to do the hypothesis testing. So in such cases, how do we deal with it? We are going to learn today a new concept of bootstrapping. So today we are going to learn a new concept, that is bootstrap. So first of all, we will learn what it is, what is the background for it, how can we find that. Then we are going to focus on the non-parametric bootstrap method, because in this we are not going to assume any distribution, or we do not make any assumptions about the population from which the sample has been taken. The other one would be the parametric bootstrap. In parametric bootstrap, as the name itself suggests, we have the distribution, we know the distribution, but it is not necessarily normally distributed. So we can consider any other distribution as well and do the hypothesis testing. So in these two different cases, for non-parametric and parametric, we will see how you can test the claim about the population mean, population variance. Likewise, if you have two sample problem, then how do you find those things? So let us begin by considering the motivation behind this topic. Suppose you are dealing with the real world challenge where the underlying distribution of your data is unknown. So you have collected the data, but you do not know the distribution from which it is coming. Now, in earlier cases that you have studied, the traditional methods cannot be applied here, because they often assume something about the distribution. We assume, last time you can recall that we considered normal distribution or maybe specific distributions. So if you have to then analyze your data, then what can you do? To answer this, we have the concept of bootstrapping, which says that it allows us to basically bypass these assumptions. Okay, it says that you do not have to consider, even if you do not have any knowledge about the assumption or the distribution from which it is being taken, you can still analyze your data and you can still test the hypothesis, or maybe later we will see how to find the confidence interval also. So what is the central idea behind this? The central idea is that your sample is very informative about the population, right? Any sample that you are taking is going to reflect the population, if provided it is a representative sample. For instance, if you want to analyze the marks of your class, so you might take a sample from there, and there you want to study the test score, the average test marks, and based upon that you want to generalize that, right? Now the problem is that how can we speak about the whole population's variability based on just one sample? Okay, because when we want to generalize our estimate or whatever we have obtained based upon, so now the question is that how do we speak about the whole population's variability based on just one sample? Okay, so in order to generalize, so the challenge is that how do we generalize about the whole population's variability based on just one sample? See, we want to make generalizations about the population based on the sample that we have selected, right? Now, when we do that, we often face uncertainty, right? Because how much can we expect our sample estimate to vary if we just take if you are going to take a new sample, right? Because we know that sample mean, if you are just taking a single sample, it will give you one sample mean, but if you change even a single observation, the next time that sample mean would vary, right? So how can we expect our sample estimate, suppose it is sample mean or the median, to vary if we take a new sample? Now this uncertainty is often measured by the variability or the standard error of the estimate. So basically the challenge now lies in estimating this variability accurately when you just have a single sample and you don't want to make any assumption about the population also. Okay. So here you can't keep on taking samples again and again. Okay. So we can in fact simulate this process by just taking samples from the data that you have already obtained. So you repeatedly do it. You take you do resampling from that data set only and keep on finding the new estimate. And when you do it large number of times, so its variability will basically build up on how our estimate might vary. So that is why by resampling from your sample, you can gather more insights. So this process is like having multiple mini copies of your original sample. Okay, so you have the original sample, now you are drawing samples from that with replacement. With replacement means that once you have taken, you have noted down the observations and then you keep it back. Okay, and then again you want to take a different sample. So this is like repeating it. You have multiple copies of your original sample only. And by examining the variability across these mini copies, you can infer the variability of our statistic that we have obtained if you would have obtained multiple samples from the population, right? So it would work in the same way as if you would have obtained multiple samples from the population. Since you cannot do that, we just have a single sample. In real life, we cannot keep on resampling again and again from the population. So instead of that, we just focus on one sample, and from there we keep on taking different samples with replacement and we make conclusions about the population. Suppose you have this random sample coming from some population and these are the realized values, right? So we use small xi's for that. Now a bootstrap sample or empirical bootstrap sample is a random sample of size n from this with replacement. So from this itself, you are going to draw a random sample again of the same size with replacement. Okay, and you can denote the ith bootstrap sample as this, right? So you can have, suppose you decide that you will take 100 bootstrap samples, so n in this case would be 100. So first of all, you will have x1 for the first sample, x11, x12, and suppose your sample size original was say 10, right? So up till 110, right? Or 19 maybe. Similarly, you will take for the second one, right? And likewise, it will keep on happening till the 100th sample. Okay. So for each of them, you will obtain a bootstrap sample. For instance, if this is your random sample, suppose, so what you will do? You will again resample from this and you will get your first bootstrap sample like in this way, right? Now, when you are doing it with replacement, it means that the same observation might occur multiple times also, right? So here also you might come across, suppose here in this second bootstrap, so 43 appears twice over here, right? Or you might come across any other observation as well. So here 7 appears twice, 10 is appearing twice over here, 12 is also appearing again. Okay. So in this way, you can see that same observation might be repeated, and by analyzing this bootstrap samples, you can talk about the variability, and then obviously you could finally generalize it. So basically how bootstrap works is that you are going to take the bootstrap samples from your original sample and you will calculate the statistic of each bootstrap sample, right? From each bootstrap sample, suppose you have taken the first bootstrap sample. So just let me write first bootstrap sample. So suppose you calculate your x bar, so you have calculated x1 bar. For the second one, again you will calculate x2 bar, and you keep on doing up till 100th one, right? So for each of them you will calculate the statistic in which you are interested. Now you will look at the sampling distribution of that statistic, and finally you can estimate the uncertainty, because it will enable you to make informed inferences about the population. So we will see how it can be done. If T is basically the desired statistic that you want to compute, right, sample mean, then TIs will basically denote the statistic computed from the ith bootstrap sample. Okay, so this is from the original one, right, T, and then for each of them you will have T1 to T100, suppose. Fine. So here you can see that each TI is calculated from a sample, right? That's meant to basically mimic that is being drawn from the original population. Okay, so if you take the average of these, it should give you an idea about the T itself. Okay, so here you can see that T is well approximated by TIs, and as well as its variability can also be approximated by this. So Bootstrap here, if you go by the term itself, so it basically refers to pulling oneself up by one's bootstraps, right? So it is just a metaphor. So in statistic, basically here, if you can relate that, so it means that we are trying to infer from the data itself, right? We use data to inform us about itself, and we can enhance our estimates based upon that sample itself. So that is why the term bootstrap is used over here. Now we are going to consider the first situation where we are going to test for the single mean. Suppose you are interested to test this two-tailed hypothesis, that mu is equal to mu naught and versus this, right? So we have seen this earlier also, and we made the assumption that it is coming from normal population. Now we want to assume that it is not coming, we do not have any idea about the population. So first of all, we are learning about the non-parametric bootstrapping or non-parametric hypothesis testing. Let the observed sample be x1, x2, xn. Next, what we will do is that you will take this sample mean. Based upon this sample, you will calculate the sample mean, and then you will calculate this statistic that you want to find out. T would be x bar minus mu naught. So suppose if if your null hypothesis was that mu is 2 and alternative is that mu is not equal to 2, then mu naught basically is 2 over here. You have the data, so you can find out what is your sample mean also. So you can easily find out what is the T. Now you will generate n bootstrap samples from the observed sample. From what you have obtained here, you will keep on taking bootstrap samples. It means that you are going to resample with replacement. You are going to take these many number of samples again and again from this with replacement, and we can denote this xi bar as the mean of this ith bootstrap sample. So if you have the first bootstrap sample, so it will have x1 bar, second bootstrap sample, so it would be x2 bar, and so on up till nth one. So let us suppose it is n is 100, so x100 you will get. Now what will be Ti? So first one, it will be T1, so T1 would be x1 bar minus mu naught. So mu naught suppose is 2, it will calculate this. Again for the second sample, it will calculate its mean, it will then perform this operation, so x2 bar minus 2. Again it will keep on going up till the 100 one, and you will have the 100 sample, you will calculate the sample mean, and then you subtract 2 from it. Next what we see is this an indicator function over here. So indicator function, and here you have the absolute value of this observed statistic that we have here, and this is the absolute value of the bootstrap statistic. So now this indicator function will take value 1 if your absolute value of this is greater than the absolute value of the observed one. So this indicator function basically counts the number of times the absolute value of this bootstrap statistic is as extreme as or more extreme than the absolute value of this. or this is your bootstrap statistic and this is your observed statistic. So it is going to count the number of times the bootstrap test statistic is as extreme or maybe more extreme than the observed statistic. Because whenever it is more, it is going to give you 1, right? It will compare each of your T1 to T100 with this T, right? You have found out this T value. It is going to compare each of these again and again. And whenever the absolute value of this is greater, it will add up over here. It will be 1, otherwise it will take 0. Suppose for the first sample it is 1, for the second sample it might be 0 and 1 plus 1 suppose, and you will get certain number over here. Now what you will do? You can take the proportion of that. So that is basically your p value. So n is the total number of bootstrap and I is basically it is the count where this absolute value is greater than this. So how many times basically the bootstrap statistic is more extreme than the observed test statistic. So here p value is the proportion of the TIs that are as extreme or more extreme than the observed ones. Now you will compare your p value with alpha. So you will reject the null hypothesis if this p value comes out as less than this predefined value. Otherwise, you conclude that you do not have enough evidence to reject the null hypothesis. Okay, so the steps are very simple. You just have to know the process and you can replicate this. Since here we are working with single mean, so that is why we found the point estimate over here, that is x bar or the MLE. So you might work with something else also. Here suppose I say that I am interested to test the variance. In this case what it will be, the procedure would remain the same with just the difference that here now instead of the sample mean you would be working with the sample variance. You have a sample, from the sample you can easily calculate the sample variance. Now you will subtract these sigma naught square. Suppose sigma naught square is 2. Same thing we can consider. Now likewise we are going to generate n bootstrap samples. We are going to resample again and again from this with replacement. And for each sample we will calculate the sample variance and then we will calculate TI. So TI basically means from that sample variance we are going to subtract sigma naught square. So T1 would be S1 square minus sigma naught square. So S1 square we will calculate from that corresponding sample. Likewise T2 would be S2 square minus sigma naught square. And likewise we can keep on doing. So obviously you do not have to do these things by hand. It will be done using any software where these steps won't hardly take a minute. So we will see in the next lectures how you can perform this in Python. So you just have to follow this algorithm and the corresponding code for it, and you will get the answer. So here it will be the 100th sample variance and you will subtract. Next what you will do? You will compare the absolute values of these TIs with the absolute value of this T that you have already obtained. You will see what is the count for this, that when this is more than this particular observed statistic. That is basically your indicator function we are using. Finally, what will be your approximate p-value? It will be I over n. So this is the proportion of observing that this TI observed bootstrap statistic is more extreme than your observed test statistic. So finally, you can reject the null hypothesis if your p-value, so this should be p, okay, we are using this, so p-value is less than alpha. Otherwise, you will conclude that you do not have enough evidence to reject the null hypothesis. Now, suppose we consider the two sample problem and you are rather interested in the difference of the two means and that the difference of the two means is not equal to 0. So, in bootstrapping, we deal with the two-tailed test only. So, here again, if you have two populations, suppose this is your population 1 and this is your population 2. So, from here you will take a sample. So, that is your x1, x2, xn, and from here whatever you take, this sample is y1, y2, yn. Now, you have taken this Now what will you do? Since it is talking about mean, it means from here I have to calculate x bar, and from these values I will calculate y bar. So what will be your observed t? So that will be basically x bar minus y bar. Because hypothesized mean, if you are subtracting, that is in fact 0 over here, because d naught is 0 in this case. If you remember, use the previous notation, so that is 0. Anyhow, it is going to cancel if you take any other value. So we can just simply write it as that t is the difference between the observed samples. Now you can generate and bootstrap samples from both the observed samples. Okay, so from this also you will start taking different bootstrap samples, and from here also you will take. So whatever from here, it will be xi bars, and these ones will be denoted by yi bars. So if x1 bar will be found out for the first bootstrap sample and y1 bar, so you will get your t1, first bootstrap statistic. So t1 would be x1 bar minus y1 bar. Likewise, you will obtain the second one, and it will be y2 bar. Again, t2 would be x2 bar minus y2 bar. This will keep on continuing till your last bootstrap sample is taken. Suppose it is n only, so yn. This is basically your, for the last one you will calculate the differences. And now finally you will look at the absolute values of these and the absolute value of this. You will see for how many number of times, in how many occasions out of n, right, it is happening that this value is more than this t, observed test statistic. Okay, so for that we use the indicator function as we have defined over here, and now you can finally calculate the p-value, that is the proportion. And then finally you reject the null hypothesis if your p-value comes out as less than alpha. So that is the usual process that we do. Otherwise you conclude that you do not have enough evidence to reject the null hypothesis. So this is how you can do for your means. Likewise, if you are interested in comparing the variances, so same way, only the difference would come that instead of mu1, mu2, you will have sigma 1, sigma 2 square. Instead of the sample means, you will be working with the sample variances, s1 square or s2 square maybe. And here also again same thing. From here the steps would be same. So let me just show you. Suppose you are interested in the difference of the two variances. So you write this. You will calculate the two samples from the populations that we know. Now these will be the corresponding. So this is the sample. I can calculate the sample variances for these two, s1 square and s2 square, and based upon this I can calculate the observed test statistic t. Now I will keep on resampling from that with replacement. So you will generate n bootstrap samples. For each of them you will have si1 square and si2 square, right? Because the one coming from here is s1. So for the first sample it will be i1 square. Likewise it will keep on going. Similarly here what you obtain, these will be si2 squares. You will get these how many number of times? N, this capital N number of times. Now once you have these observations, these values, you can compute the corresponding bootstrap statistic over here, Ti. Finally you will compare and you will find the approximate p-value. And finally you can conclude whether to reject or you fail to reject the null hypothesis depending upon your p-value. So this is how you can do the hypothesis testing where you do not have any idea about the population. So here you can see that we are just taking a random sample, right? We are not making any assumption about the distribution. It is free from any distribution, or we are not making any assumptions also. We are just working with the sample that we have and we are continuing ahead with that. So if you want to find out any other statistic also, right, instead of mean and variance, you can just apply this procedure and you will get the answer. Okay, so now in the next lecture we are going to see how do you do these in Python. Okay, once that is clear, then we will move on to the parametric concept. Thank you.